Hello everyone. Let's see the fifth problem. Reachability query. Uh, a directed graph consists of n nodes and m edges. Your task is to answer q queries. Can we reach node B from node A? Here n is up to 10 to the power 4 only. So 5 into 10 to the power 4. So we can do kind of n square. Uh, and here there are q query. Let's see that sample. So this is the graph, directed graph. There can be a cycle. So can we reach node 1 from node 3? Yes. Can we reach node 4 from node 3? No. Can we reach node 2 from node 4? Yes, from this path. So here you can see that in this component 1, 2 and 3 you can reach each node from other node. Like you can reach node 1 from node 3 or node 2. You can reach node 2 from node 1 and 3, node 3 from node 1 and 2. So this is called a strongly connected component. Strongly connected component is basically in that component you can reach each node from other node. So the given query can be transformed into uh, other type basically. So what let's first uh, convert the given directed graph into the given directed graph into other graph, like transform this graph in directed acyclic graph. So first find all the strongly connected components and replace this component with a super node. And like there are two strongly component in this graph, so replace this with 4 and this with, let's suppose, 1. You can now, if we get a query from this strongly connected component to this strongly connected component, like if we get a query from node 1 to node 4, which is equivalent to getting a query from node 1 to node 4 in this graph. Like for example, if we are asked to can we reach node 4 from node 3, we can, what we can do, we can find the node corresponding, super node corresponding to this component, which is this one, and super node corresponding to this node, and we can do the same. Like if we want to check whether node 3 can be reached from node 4 is similar to node 1 can be reached from node 4. So the question converted to first first building this graph, and then answering the query. Now let's suppose that we are given this graph, like we have somehow built this graph which is directed acyclic graph. So let's suppose 1, 2 and 3 and 4. Now you can now if there is a query whether we can reach node 4 to node 4 from node 1, then we have to do it optimally. So how we can do it, basically if we find the topological ordering of new graph this new graph and uh, we maintain a bit set corresponding to each node, and this bit set is of length n, and if the bit is 1, then it means that node corresponding to that bit is reachable from the node 1. If that bit is 0, then it is not reachable. So in this problem, the bit set is basically we can reach node 1 from node 1, node 3, node 2 and node 4. For this is basically uh, we can reach node 3 and node 4 only. So now how to calculate this bit set? So we can first calculate the topological ordering of this new graph, and we can go in reverse order, like reverse topological order, and for each node iterate over all its child and take the end, take the or of these nodes, or of these nodes, like or of the bit set corresponding to these nodes, and set the bits corresponding to 1 also, and to build the bit set for current node. So let's see the code. Let's summarize the problem, summarize the solution. First, we are given a graph. Let's suppose this is the graph, something like that. We first convert it into uh, some concise representation, like we converted each strongly connected component into a super node, and finally we get a directed acyclic graph. And what we did is basically find the topological ordering of this node. Let's suppose this is the topological ordering, and we iterated from right to left, and for each node we iterated over its for each node we iterated over its child, and taking the or of the bit set corresponding to that node, and also setting the bits corresponding to the current node. And for now we can answer each query in O of 1. So let's see the code. First, I'm taking the input n, m, and q. I'm taking decency list. Now I have this template, like which is for a strongly connected component. This is one indexing, and basically do something, and it finally it basically this adj underscore scc is basically the concise representation of the given graph. It's a strongly connected component representation. So I am basically creating an object of this scc, and I'm basically scc contains a vector root nodes, which is basically what is the uh, id corresponding to that node. I mean this, like what is the name of this node. This is for, like in 1 2 3 it can either be 2 3 or 1, it doesn't matter. So we are marking all the root nodes here, scc to root nodes, mark contain all the root nodes. And I'm doing, I'm basically calculating the topological ordering of this adj scc, like strongly connected component representation. And I'm going in reverse order, and what I'm doing is basically uh, taking the current node and setting the that bit, and I am editing over its child, and basically taking OR of all the nodes. Now for each query, whether we can reach node V from node U is basically similar to the node corresponding to the, like super node corresponding to the current node. uh, like we are replacing U with the super node corresponding to that node, and similarly for V. And if we can reach from U to V, like from that strongly connected to component to other strongly connected component, then we can also reach from node U to V also. So if the bit is set, if the bit in the bit set of U, if the bit V is set, then our answer is yes, otherwise it's no. And one thing you have to do is basically include this flag, like O3 or fast and pop count, like thing. Thank you.